All right, 3.1, defining the derivative. Calculus is important in all branches of mathematics, science, and engineering, and it is critical to analysis in business and health as well. In this chapter, we explore one of the main tools of calculus, the derivative, and show convenient ways to calculate derivatives. We apply these rules to a variety of functions in this chapter so that we can then explore applications of these techniques. And here's just a quick timeline. A team of British researchers from universities of Exeter and Manchester had asserted in 2007 that the true credit for invention of calculus lies in the Kerala School of Astronomy and Mathematics. And here we can look at the timeline of when we had Descartes, 1596 to 1650, Cavalieri, Fermat, Wallace. We can go through all these different people in mathematics and the areas at the time periods, what was going on. So there's just kind of a brief history or a little bit of a timeline to give you an idea of how far back calculus goes. Okay, defining a derivative. Let's let f be a function defined on an interval containing a. If x is not equal to a, is in the interval, then q is a difference quotient. So here we're looking at a difference quotient, which is basically a slope, f of x minus f of a over x minus a. So we're looking for, if we're looking at what we're looking at, here's that slope of a secant line. Okay, and sometimes you'll see where h is used. So if h does not equal 0 is chosen so that a plus h is in the interval, then q is the difference quotient with increment h. So these two are the same thing. It's just a different way of annotating. Are we looking at x and a, or are we looking at a plus h and a? So it all is a distance is what we're looking for. Here I have, if we look at the first one, there's my x, there's my a. So f of x minus f of a over x minus a. Here I have f of a plus h minus f of a. And if we look at the difference, a minus a plus h, then we'll get h, or a plus h minus a. We'll get h. So that this is the difference between these two distances here, these two values. Okay, so definition of a secant line. And here you can click on the image, then move the blue points to create the secant line from a to f of a to x to f of x. Sorry, a to f of a to x to f of x. The tangent line at the point a to f of a. Note that the closer the 2 points are, the closer the equations of the secant and tangent lines are. So let's see if we can look at this here. All right, so here we have our function here. And as I move, so again, here's my secant line, the dotted line, and you can see the red line is the tangent line. As we move these points closer and closer to each other, you can see our secant line and tangent line become the same line. We can go back and you can see there's my secant line and my tangent line. So again, as they get closer and closer to each other, they become a tangent line at this point. So that's kind of nice to play around with there and see what's going on. Okay. So in mathematics, infinitesimals are things that are so small that there's no way to measure them. This idea was used to consider the change in x is so small, but not zero, that it cannot be measured. The idea was criticized by Berkeley as ghost of departed quantities. They assume that we have a point, x, f of x, and x plus d of x, and f of x plus d of x are very close to each other. In other words, d of x and dy equals f, x plus d of x are infinitesimals. They assume that the slope of the tangent line to the graph of f of x would be given by dy over dx. So change in x over change in y is what we're looking at. So this is notation, and you're going to see that here, this dy dx. That is a slope, right? Change in y over change in x. That's what we're looking at here. So let's look at some examples. What is the slope of the tangent line at x for this particular function, x cubed plus 2 of x? So we let y equal f of x, which equals x squared plus 2x. And then note that x plus d of x cubed. So if we plug this into our function, what do we get? Or what are we looking at here? What is x plus d of x cubed? And this is what that is if we cubed that and simplified it. So the change in y equals x cubed plus 3x squared dx plus 3x dx squared plus dx cubed plus 2x plus 2 dx minus x cubed plus 2x. So there's the top, or the numerator, right? Remember what we're looking at. But since dx is very small, dx squared and dx3 go to 0. So we can see that f of x plus dx is approximately x cubed plus 3x squared dx plus 2x plus 2 dx. Change in y equals dy. So that's where that dy equals the change in y. And we're looking at a difference. Okay. dy equals 3x squared dx plus 2 dx. We can factor the dx out. dy dx equals 3x squared plus 2. So for example, x equals 1. What do we get? Well, when we plug 1 in, I get 3 plus 2, which is 5. So once we find the derivative, that change in y, change in x, slope, and this is kind of an ugly way to do it, but the principle's the same. Okay, and this is what was done before the idea of a limit was invented. And you could see this could get pretty ugly looking at those dx's. So dx, as dx approaches 0, then the slope of the secant line, that's what this means, is the change in y over the change in x. Slope of the tangent line, dy dx. Okay, so remember the secant line is the line we're kind of estimating what it is. So here's my secant line, and here's the tangent, here's the tangent line. And the change in x equals dx, the change in y equals dy. So we're looking at the horizontal change and the vertical change. So as the values of x approach a, the slopes of the secant lines provides better estimates of the rate of change of the function at a. The secant lines approach the tangent line at a. So again, the closer and closer the secant line gets to a, it's going to get closer and closer to the tangent line. So if it's coming from this direction, you can see as it comes closer and closer, it becomes the tangent line as it gets to a. So we're looking at the limit of a difference quotient. Remember, difference quotient is just a slope, change in y over change in x. We're going to take the limit of it as it approaches x. As x approaches a. Okay. As the values of h approach 0. Now we're looking at this particular definition, or this particular quotient function. Again, as it gets closer and closer to 0, the slopes of the secant lines are better estimates of the rate of change of the function at a. That secant line approaches the tangent line. It gets closer and closer. So as h gets closer to 0, we see that our secant line gets closer to our tangent line. So let's look at the definition. Defining a derivative. Let f of x be a function defined in an open interval containing a. The tangent line to f of x at a is the line line passing through the point a, f of a having slope. And here's again the slope of the tangent line equals the limit of the function f of x minus f of a divided by x minus a. That's our quotient function, as x approaches a. So that's our difference quotient, I should say, as x approaches a. And it provided this limit exists. And that's important as well. So f prime of a, that's a way we can write the derivative function notation, equals the slope of the tangent line, which is the limit of the difference quotient. So again, equivalent, we can look at this using the h, and it's the same thing. We're looking for the derivative, which is the slope of the tangent line, which is the limit of the difference quotient as h approaches 0 for this particular definition of the limit. So, and different books use different definitions, but they're similar. They may use different variables in here as well. So let's look at an example. Find the equation of the tangent line, or the line tangent to the graph f of x equals x squared at x equals 3. So we're going to take our difference quotient and we're going to take the limit as h approaches 0. So first of all, I need to figure out what is f of a plus h and what is f of a. So here's our function. So, and we're looking at x equals 3. So we'll plug our 3 in for our x. So that's going to be 3 plus h squared. That is my f of a plus h minus 3 squared. So I put in, there's my 3, put my 3 in for my function. Okay, think of this as x and an x because that's the variables we're looking at. So this is f of x plus h minus f of x. So we plug it in, simplify, okay, because if we try to take the limit, it's going to be undefined, but we can simplify it a little bit here. So here, if we try to take the limit, so let's look at what we can do. Look how our h's go away. Then I have the limit of 6 plus h as h approaches 0, and I end up getting 6. So y minus f of 3 equals the slope of the tangent times x minus 3. This is that point slope formula. Y minus y2 equals m times x minus x sub 1. So that's all this is the point slope formula. And we come up with our equation of the tangent line. And we can look here at a parabola. So we have the limit of x squared minus 9 divided by x minus 3 as x approaches 3. So what's going on as x approaches 3 right here? There's that tangent line. So again, as we look at the limit as x approaches a, well, that was 3. We found that was 3. If we go back to the beginning, we're approaching 3. So we're taking the limit of x squared minus 9 over x minus 3, the limit of a difference quotient. If we look at it from using the different limit, which I think, in my opinion, this one's not quite as bad as with the h's. But you can see we come up with the same answer whether you use this definition or this definition. Either one is fine. Okay, so let's look at another example here. This says estimate f prime of 3. So this is using the calculator, so we can put in our function after we substituted, set up your table. You can see we have 0.03 here. We want these fractions here as we're getting closer and closer to 0. As it's approaching 0, where are we going to? And you can look 5.99, 6.01 from the left, from the right, from the left, from the right, and it's going to 6. So that would be a good estimate for f prime of 3 using our TI-84. Okay, let's look at another example. And again, I really like this method a little easier. The h's sometimes can be confusing. We want to let f of x equals 3x squared minus 4x plus 1. We're going to find f prime of 2. So we're going to find the limit of this difference quotient. Plug in f of x minus f of 2. Well, what is f of x? That's 3x squared minus 4x plus 1. What is f of 2? Well, plug 2 in here and I get 5. On the bottom is x minus 2. There's my a, remember. Factor, we can simplify this. 3x squared minus 4x minus 4. Factor it. And these will cancel. Now try the limit substitution again, and we end up with 8. And I'm going to just go ahead and put the other method up here. You can see we still get 8, and if you're interested, pause the video and look through it. But again, I really kind of like using this one better. It doesn't seem quite as confusing. Instantaneous rate of change. That's what we're finding here. We're finding the derivative is an instantaneous rate of change at time t equals a, is the derivative of the position function s of t, used a lot in physics and many sciences at t equals a. So we're just going to use some different variables. V of a is velocity, which equals the derivative of the position function. So instantaneous velocity, again, is a derivative of the position function, which is the limit of the difference quotient as t approaches a. So s of t minus s of a over t minus a. So instead of f of x, we're using s of t, just variables, just notation. The instantaneous rate of change of temperature at time t is the derivative of the temperature function. So here we use the derivative of the temperature function with the capital T of t. The instantaneous rate of change of profit at x equals a is the derivative of the profit function P of x at x equals a. And so P prime of a is the derivative of the profit function, which is the limit of the difference quotient. So these are just different ways you might see the difference quotient. They're just variables, so don't be surprised. It may not be f of x. It could be s of t if we're talking about position. It could be t of t if we're talking about temperature function, profit function P of x. So these are all things you may see. So don't be surprised.